All right, welcome in everyone. I'm absolutely thrilled you're here. Today, our main goal in this explainer is to completely demystify the computer. We aren't just going to look at it as some cold, boring metal box. Instead, we're going to explore it like a living, breathing system, starting from its physical hardware components, all the way up to its digital mind.
Seriously, take a second and just think about this. Have you ever wondered what is actually happening inside the device you are watching this on right now? I mean, we hear terms like hardware, software, processing, and memory all the time, right? But how do these totally abstract concepts actually come together to form the very real digital device sitting right in front of you?
Okay, let's dive right into this. Here is our roadmap. 1. The fourth generation revolution. 2. Giving the computer senses. 3. How the machine communicates. 4. The computer's memory bank. 5. Navigating the digital mind. And finally, 6. Mastering your file management.
Starting with Section 1, the fourth generation revolution.
So every living system needs a brain, right? And to fully appreciate the modern digital brain we have today, we kind of have to look back. Back in 1956, the second generation of computers used transistors. Now these were a massive improvement over those old hot vacuum tubes, acting as switches to amplify electronic signals. But computers were still, frankly, huge. By 1964, the third generation introduced integrated circuits, or ICs, which made things smaller and a whole lot faster. But then, in 1971, everything changed. We entered the fourth generation with the invention of the microprocessor.
So what exactly is a microprocessor? Well, it's a single, incredibly complex chip containing the entire central processing unit, or CPU. The absolutely crucial point here is that by condensing the computer's entire processing brain onto one tiny piece of silicon, technology was finally able to move out of those massive corporate labs and actually into our personal homes. Without the microprocessor, the whole personal computer revolution literally wouldn't exist.
Which brings us to Section 2, giving the computer senses.
Okay, so now that our machine has a highly capable microprocessor brain, it needs a way to perceive the world around it. The most basic way we give a computer its senses is through manual input devices. A traditional wireless mouse setup, for instance, uses radio frequencies or Bluetooth to send our hand movements to a little USB receiver. Meanwhile, a laptop touchpad accomplishes the exact same thing. It simulates human touch to direct the cursor, select icons, and let us physically interact with the digital environment.
But let's be real, manual input can be pretty slow. To speed up that sensory input, we use what's called direct data entry. So instead of a human manually typing in a product number or price at the store, a hardware device, like a barcode scanner, uses optical technology to instantly read a series of lines, query a database, and fetch all the details automatically. It requires way less human interaction and drastically reduces errors.
And we see this automated sensing everywhere, don't we? When you insert your card at an ATM or a checkout terminal, you're using a magnetic stripe reader. The computer is instantly reading the encoded data on that magnetic stripe to retrieve your account info and process your transactions securely and in the blink of an eye.
And for tasks that require extreme pinpoint precision, we have devices like light pens or graphic tablets. Just think about graphic designers using a Wacom tablet, right? They bypass the clumsy keyboard entirely. They're translating the natural physical strokes of their hand directly into digital data on the screen. It is just a seamless bridge between human intention and computer comprehension.
Let's move on to Section 3, how the machine communicates.
If input devices are the computer's senses, well, output devices are its voice. And the most fundamental output device is the monitor. Older cathode ray tube, or CRT monitors, you probably remember those, fired a beam of electrons onto a phosphor screen. They were heavy, they consumed massive amounts of power, and they generated a ton of heat. Now, contrast that with today's light-emitting diode, or LED monitors. These use liquid crystals and tiny grouped diodes to produce crisp, highly efficient, and incredibly vibrant visual output, all without taking up half your desk.
And this brilliantly illustrates how output isn't just a personal one-on-one experience. Output devices like projectors take the video signal, magnify it, and display it on a massive scale. This allows the computer to share its thoughts and digital workspace with a whole audience all at once, whether that's in a tiny classroom or a giant conference hall.
That takes us to Section 4, the computer's memory bank.
Okay, so we've got a brain, we have senses, and a voice.
Now our machine needs to retain information, and it does this through storage devices. For decades, the undisputed king of long-term computer memory has been the hard disk drive, or HDD. The internal anatomy of a hard drive is essentially a high-tech record player. Inside an air-sealed metal casing, you have magnetic platters spinning on a spindle. An actuator arm moves a tiny read-write head across these platters, physically magnetizing microscopic north and south poles to represent binary ones and zeros. Honestly, it's an incredible feat of microengineering.
But the HDD has a pretty major rival now. Let's look at the classic modern tech debate: HDDs versus SSDs. Hard disk drives give you massive, affordable capacity, sure, but because they have physical moving parts, they are slower and definitely more prone to mechanical failure. Solid-state drives, or SSDs, on the other hand, use NAND flash memory chips. With absolutely no moving parts, SSDs are lightning fast, highly durable, and consume way less power. Unsurprisingly, they are rapidly becoming the absolute standard for the computer's primary memory bank.
But hey, don't count out the mechanical hard drive just yet. Here's a wild fact for you. The speed at which a computer can access data on a traditional hard drive depends on its revolutions per minute. While your standard old laptop drive might spin at about 5,400 RPM, some high-performance server-based hard drive platters spin at a dizzying 15,000 revolutions per minute just to keep up with the data demands. That is incredibly fast.
Next up, Section 5, Navigating the Digital Mind.
So we've built the physical body of the computer, the hardware. Now let's take a look at the software interface. The graphical space where we actually interact with the machine's consciousness is known as the desktop. It's your main interface screen. Environments like Windows 10 provide a really intuitive visual workspace. Instead of typing complex lines of code just to tell the microprocessor what to do, we use graphical user interfaces, or GUIs. We have a taskbar at the bottom acting as an anchor, and a start screen filled with applications and dynamic tiles. This whole setup acts as our super user-friendly gateway into the machine's complex capabilities.
Let's move to this next view and see how this builds into an efficient workspace. The modern desktop isn't just static, it's highly customizable. Users can drag, drop, and group animated, colorful tiles right into specific folders on the start screen. You can resize them, unpin what you don't need, and mold the computer's interface to perfectly match your specific workflow. And finally, Section 6, Mastering Your File Management.
Listen, having a powerful digital mind is totally useless if you can't actually find anything inside it, right? Effective file management is all about systematic organization. It's the difference between a clean desk and a chaotic, stressful pile of papers. You need meaningful folder organization, structuring things by project or category. You absolutely must use consistent, descriptive naming conventions so you know exactly what a file is before you even open it, perhaps even utilizing specific file extensions so you know the format. Always perform regular backups to prevent catastrophic data loss. Use file compression to shrink down massive folders and run disk cleanups regularly to remove temporary files that are just clogging up your system's memory.
And beyond just the files, you also have to manage the physical drive itself. This happens in a few foundational steps. Step 1 is partitioning. This is logically dividing up one physical hard drive into separate, distinct digital sections. Step 2 is formatting, where you set up a specific file system, like NTFS, so the computer knows exactly how to store data there. And step 3 is defragmentation. Actually, think of it this way. Over time, as you save and delete files, parts of files get scattered all across the disk. Defragmentation neatly rearranges that scattered, fragmented data, keeping the computer storage running incredibly smoothly and quickly.
Well, we have covered an immense amount of ground today, literally building a computer from the microprocessor up to the desktop interface. But before we go, I want to leave you with a provocative thought. We've been talking all about the 4th generation today, but we are currently entering the 5th generation of computing. Driven by ultra-large-scale integration and parallel processing, these new machines are moving way past simply executing our coded instructions. They are integrating artificial intelligence, they're understanding natural human language, and they're beginning to actually make decisions. So now that you understand the strict, structured anatomy of today's computer, ask yourself, what happens to our relationship with this machine when it finally starts thinking for itself? Definitely something to ponder. Thank you so much for joining me on this explainer today, and as always, keep learning.